Hello, my name is Sangmin, an undergraduate student at Seoul National University of Science and Technology. Today, I will be presenting our study titled Comparative Study of Structure from Motion on Construction Site. Let me begin by introducing the background of this study. In the construction industry, progress monitoring is a key task to ensure project quality, schedule compliance, and safety. Traditionally, this has been done through manual inspection, which is often time-consuming, error-prone, and inconsistent. As a more advanced solution, recent studies have adopted 3D modeling technologies for inspection and monitoring. Among these, the use of LiDAR and laser scanners has gained attention because they provide highly accurate and detailed spatial information. There are some examples of how these technologies have been applied. First, Hugh et al. Utilized LiDAR to scan 3D surfaces of open cast quarries, enabling detailed slope stability analysis through geological modeling. Second, Wang et al. Employed laser scanners to track and model heavy construction equipment such as tower cranes in near real time. However, these methods come with several limitations. They are expensive, bulky, require extensive training to operate, and take significant time to scan a site. Because of these limitations, they are less practical for dynamic and fast-paced construction environments. As an alternative to expensive laser-based equipment, methods that reconstruct 3D models from 2D images gained attention in the construction industry. While these methods may offer lower accuracy compared to specialized sensors like LiDAR, they provide major advantages in terms of accessibility, ease of implementation, and reduced scanning time. Among various image-based methods, structure from motion stands out because it can reconstruct not only 3D geometry but also estimate camera poses, including position. So what exactly is structure from motion? It is a computer vision method that reconstructs 3D point clouds and estimates camera motion from 2D image. There are two main types, incremental and global SFM. Incremental SFM builds the model step by step by registering one image at a time, while global SFM estimates all camera poses simultaneously. In this part, I will briefly introduce the incremental SFM pipeline. The first stage is correspondence search, where we find overlapping images and extract matched features using descriptors like SIFT or learned features. We then filter incorrect matches using geometric verification techniques like Renza. The result is a graph of verified image pairs ready for reconstruction. Next is the incremental reconstruction phase. We start with an image pair for initialization, then add new images one by one using perspective and point with 2D 3D correspondences. Triangulation is used to create new 3D points from matched features, and bundle adjustment globally refines all poses and points. This process is repeated until all images are added. Now let's look at global SFM, which estimates all camera poses in a single batch using rotation and translation averaging. This avoids the drift that may occur in incremental SFM and ensures more consistent global results. VGGSfM takes this a step further by replacing all components with deep learning modules. It includes a key point tracker, a pose estimator and triangulator, and a bundle adjustment network. All modules are trained jointly with supervision, allowing for fast and robust reconstruction. The VGGSfM pipeline starts with 2D point tracking, linking the same feature across images. Then a deep network simultaneously estimates all camera poses, avoiding local inconsistencies. This global pose prediction is a major strength of VGGSfM. Next, the system triangulates 3D points based on the predicted camera poses and 2D tracks. Finally, the bundle adjustment refines both structure and motion using backpropagation. The network is trained by minimizing reprojection error, making the entire SFM pipeline trainable from data. Several prior studies have applied SFM in construction sites. One used a floor-wise hierarchical approach for indoor scenes, while another reconstructed outdoor sites using drone images. However, these methods often rely on a large number of images, high overlap, and manual post-processing. In our study, we aim to test modern SFM systems under realistic constraints, a small number of images, and minimal pre-processing. Our goal is to evaluate their practical performance and limitations in actual construction environments. We conducted our case study in an actual construction site using an Insta1X2 fisheye camera to capture 360-degree images. These spherical images were then converted into perspective views using panoramic to perspective transformation. We generated two types of view, front-facing and right-facing. In total, we extracted 26 perspective images. To quantitatively evaluate the performance of each SFM method, we use three metrics. First, mean track length represents the average number of images in which each 3D point is observed. A higher value indicates stronger feature connectivity across views. Second, mean observations per image measures how many 2D observations are generated per image. This gives insight into feature richness and tracking consistencies. Finally, mean reprojection error quantifies the geometric accuracy of the reconstruction by comparing the observed 2D feature points and their reprojected locations. A lower MRE means higher geometry. We compared two SFM methods, COLMAP, an incremental pipeline, and VGGSfM, a deep learning-based global pipeline. VGGSfM generated over 5 times more 3D points than COLMAP and completed the reconstruction about 20 minutes faster. This shows that VGGSfM is more suitable for large-scale or time-sensitive SFM tests, with the MTR difference likely due to dataset-specific factors. Here we compare the qualitative outputs. VGGSfM produced a more complete and coherent 3D reconstruction of the room, especially in the central floor area, which appeared fragmented in the COLMAP result. While COLMAP captured sharp edges and distinct patterns effectively, VGGSfM provided a more balanced and uniformly distributed point cloud across the wall surface. However, both methods showed limitations in occluded or textureless areas. In addition to COLMAP and VGGSfM, we included Mushroom and OpenMVG to evaluate their potential as lightweight pre-processing tools for camera pose estimation. These tools are not primarily designed for dense reconstruction, but they are widely used in pipelines where fast pose initialization is required. However, they reconstructed far fewer 3D points for Mushroom and OpenMVG, making them less suitable for detailed modeling. Despite their sparse and incomplete 3D reconstructions, both Mushroom and OpenMVG were able to successfully estimate camera poses with high speed, making them particularly suitable for use as lightweight pre-processing modules in pipelines that require initial pose estimation for dense reconstruction methods such as MVS or NURF. To conclude, our comparative study demonstrated that VGGSfM outperformed COLMAP in terms of reconstruction density, accuracy, and processing time. Meanwhile, Mushroom and OpenMVG were much faster under 30 seconds, making them highly suitable for fast pose initialization, but less effective for dense 3D modeling. However, there are several limitations. SFM inherently relies on 2D images, making it vulnerable to occlusion and lighting variation. Our evaluation was limited to a single room, and transitions across rooms were challenging due to the lack of overlapping features. Future work should focus on multi-room integration, improving robustness and in challenging indoor conditions, and supporting full-site 3D modeling for construction monitoring and quality control. Thank you for listening my presentation. If you have any questions, feel free to contact me.